We've already seen what it means for Eve to be ignorant about the key. The key was uniformly random and uncorrelated from Eve. Let's suppose now that we have a classical string, a key, for example k or string x, produced by a randomness box that is not uniformly random. Is this string still useful for cryptography? We will see that the answer to this is yes. In fact, next week we will explore extensively how to turn imperfect versions of randomness into almost perfect ones. And in order to accomplish this, we first have to quantify randomness. To make it simple, I first want to consider the case where there's no eavesdropper Eve. We are just interested in a classical string x generated by a randomness generation box. I push the button of this box and it generates a string x1 up to xn. Now, in the ideal case, the string would be uniformly random, meaning that the probability of obtaining a string x is 1 over the number of possible strings, namely 2 to the n, where n is the length of the string. Or if I want to write the probability distribution as a quantum state, it is the maximally mixed state on n qubits. Of course, you might say, if I want to quantify the randomness of another state, for example, this one, where I'm uniform everywhere except the last bit is always 0, then maybe a useful measure to quantify randomness would just be the trace distance between this situation and the ideal one. The trace distance is very useful in cryptography if we are already very close to the ideal case. Epsilon close, where epsilon is so small that it's essentially negligible. However, in this case, we are not quite so close. If you remember the example for the trace distance, to distinguish the 0 state from the maximally mixed state on 1 qubit, the trace distance was pretty large. So we can distinguish these two situations very well. If we cannot use the trace distance as a measure to quantify approximate randomness, what other measures might there be? Possibly, if you come from classical computer science, or also if you come from physics, you might have heard about something called entropy. If not, you might want to skip ahead or listen anyway. The entropy that you may be familiar with is called the Shannon entropy. This entropy is defined as follows. We have minus the sum over possible string x, probability of the string x, log probability of x. So basically we're averaging over minus the log probability of x. For the ideal case, where all strings are equally likely, this entropy is equal to n. So maybe this entropy is a good measure to quantify randomness, in the sense that if I have a box that still has maybe, I don't know, entropy n over 2, this would be very useful. Imagine that my perfect box that has an entropy equal to n costs $100. And let's say that I have another box for sale which has roughly half that many bits of entropy. That's still decently large if you think of n being huge. N can be a billion. So this, even my imperfect box, has plenty of entropy. So my question to you is now, what would you bid for my box that has entropy n over 2? In this video, I'm of course unfortunately not sure what your bid was. But let me open this box for you. I will tell you that the actual probability distribution that produced the string x looks as follows. With probability half, it will output the 111 string, and with probability half, it will output one of the other strings uniformly at random. If you compute the entropy of this distribution, and I encourage you to do this, we will find that the entropy is roughly n over 2. The question is, would you be happy to use the string x that comes out of this box, and you only get to use this box once, as an imperfect key? Let's imagine that I'm actually an eavesdropper. I have sold you this box to produce keys, and I promised you, I gave you a guarantee that it has entropy n over 2. But note that my probability of guessing the key is a half. I will always guess that the output, the string x, is 11111, and I will be correct with probability half, independent of the length of the string. Nevertheless, the entropy is huge. In fact, the entropy grows with n, whereas my guessing probability is constant. So the Shannon entropy also does not seem to be a very good measure for randomness. We thus need a better measure. It turns out that in cryptography, the relevant measure is called the min entropy. The min entropy is defined as minus the log of the largest element of my probability distribution. In our example, the largest element was a half, so the entropy is minus log of a half, which is 1. So the min entropy is constant. It does not grow with n. You can think that unlike the Shannon entropy, the min entropy captures the worst case behavior. You can think that this expression maximizing over x of p of x is in fact the probability that I guess x correctly. I will always guess the most likely string, and I will be correct with precisely this probability. The min entropy is thus really minus the log of the probability that I guess the string. I hope I convinced you that the min entropy is an interesting and useful measure, and we will see that it has all kinds of nice applications in cryptography. In fact, the min entropy is exactly the quantity that tells us how many truly random bits we can, almost perfectly, produce from a randomness box with a certain amount of min entropy.